All right, just a few more people continue to roll in. But thank you everyone for showing up here on this wonderful 1st of April, where we will have a very excellent talk on metamaterial microwave absorbers, something that radio astronomers would absolutely love, by a fellow postdoc, Zhilei. And yeah, that is no joke. Thought about giving a wonderful astrology presentation or something beforehand, freak all the astronomers out, but let's get right to it. So Zhilei, whenever you're ready, take it away.
Thank you so much, Jesse. Thank you so much for inviting me. It's great I can come here to present this work we did when I was in University of Pennsylvania working with Professor Mark Devlin. So yeah, as Jesse mentioned, this is metamaterial absorber. We call it MMA for basically CMB experiments. Before diving into all these technical details, I would like to introduce something about the CMB, the cosmic microwave background. It's a mission emitted in the early universe. It contains the primordial information of the universe, and it travels all the way across the history of the universe before it was observed by us, almost undisturbed. So that's why it has taught us a lot about the basic information of our universe. So like the content of the universe, the age of the universe, etc. So the current focus on this front is actually try to detect the signature of something called cosmic inflation. If cosmic inflation ever happened, it would have imprinted a unique signature on the polarization pattern of the CMB. So this is where everyone is after to answer this kind of ultimate question. And over the past, I would say, couple of decades, there were new advancements in the CMB in terms of in the way of studying the universe, which is because the CMB photons traveled across the history of the universe. Although it was not a lot, but it still picked up a lot of information on its way. So with that, the CMB observation right now can actually help us to understand the mass distribution of the universe by lensing, and also help us to study galaxy clusters by a Science-Dovich effect, and also to constrain the cosmic ionization even. So basically, the CMB is a powerful probe to basically study a wide range of cosmological and astrophysical questions. And then I would like to walk a little history of the CMB observation. This is about like 30 years ago, and when this COBE satellite measured the frequency spectrum of the CMB. So it's a really remarkable measurement. You can see the error bar here, shown here, is like 1% of this line thickness. So not only the measurement itself is really remarkable, it's the result that's even more remarkable because it's a perfect black body. It's astonishing because this emission was emitted the earliest and also the farthest ever we can observe, probably invisible light, not invisible electromagnetic radiation. It follows the simplest physics we understand the best on Earth. That's actually another attractive point of studying CMB, because when CMB was emitted, the universe was so simple. It was linear, it was almost uniform. So a lot of this physics is simpler for us to understand the condition and also all the physics that happened then. After measuring this black body spectrum, people switched over to measuring whether different position on the sky has the same temperature. So it was tried even by Penzias and Wilson when CMB was discovered in 1965, but because of the sensitivity limitation, they didn't see it. And then COBE satellite had an instrument doing this, which made a statistical significant measurement of the anisotropy, but not enough to constrain cosmological parameters. That was actually done later by the WMAP mission, as shown here. The current state of art CMB anisotropy measurement is given by the Planck satellite. This is the map the Planck collaboration provides. So you can see different temperature at different points over the sky, but they are really faint. The fluctuation is really small. It's like a 10 or 100 parts per million over the 2.7 Kelvin temperature. So then what do we do with this map? So normally for the CMB field, people take a power spectrum. It's kind of like a 2D Fourier analysis of a map, but it's different because it's in the spherical coordinates. So instead of using 2D Fourier transform, we use spherical harmonics. So the x-axis is kind of something like frequency, but it's in this spherical harmonic kind of language, it's multiple. So the lower the multiple number it is, the large angular scale it represents. The higher the L multiple value it is, the smaller angular scale it represents. So basically on the x-axis going from left to right, we are going to smaller and smaller angular scale, larger and larger multiple value. And then the y-axis actually is the amplitude of the power spectrum. And then if we look at this, there are three kind of lines here. The top one is the temperature anisotropy power spectrum, which was the initial focus to measure the anisotropy. The middle and also the bottom one are the polarization anisotropy pattern. You can see these are orders of magnitude fainter compared to the temperature, and also the B mode, we call it, is even fainter than the E mode, which has been rather well measured. So we talked about the cosmic inflation before. The really exciting scientific goal is hidden in this CMB B mode, because if the unique pattern I mentioned earlier is actually hidden in this CMB B mode power spectrum, mainly on this large angular scale on the left. That's why all the experiments are pushing in this direction. So and then if we look at this, so look at these different measurements from different experiments, a trend we can see is actually over the past decade, or I think a decade or two, probably ground-based experiments have been pushing dramatically across the board in terms of the measurement sensitivity for this field. So you can see beyond Planck and WMAP in the temperature power spectrum, polarization power spectrum is ACT, SPT, ACT pole, polar bear, bicep, etc. Basically making the measurement across the board. So these ground-based experiments mainly kind of cluster into two sites. One is the Chilean site, which is the home of Simon's Array class ACT Simon's Observatory. I'm a member of several of those. And then there's another site at the South Pole site, which is the home of BICEP and also SPT. So this is the trend that the ground-based experiments is actually pushing the envelope in this measurement. So this work I'm presenting is actually done in the context of this new experiment called Simon's Observatory. So Simon's Observatory is a very ambitious ongoing experiment with 3 small aperture telescopes, which focus on detecting this signature of the B mode polarization from cosmic inflation, as shown here. Here, the sky coverage, 10% of the sky, focusing on detecting cosmic inflation signatures. And then there is also a large aperture telescope, which resembles traditional telescope more. So you can see this big structure, 6-meter mirrors primary, secondary, and reflects everything into the large aperture telescope receiver, which is something I worked on a lot for my work at the UPenn. This is the largest sub-Kelvin cryogenic receiver ever built. So you can see from the front plate, you can see there were like 13 units. Each of them is actually a unit like this. We call it optical tubes. I annotated here, this is a tube. It might look a little bit strange, but you will see why I emphasize this later. So in terms of science, so this large aperture telescope in complement to the small aperture telescopes, it will survey a large fraction of the sky, almost like 40%, and then basically provide the high resolution sciences like gravitational lensing and also galaxy clusters. This survey will also overlap with several ongoing and also future surveys like DES, DESI, and also LSST. So if we come back to the power spectrum plot, you can see the trend in this field is very clear. It is going deeper and deeper in sensitivity. Basically, you can see 30 years ago when COBE was launched, the result was above the chart. You can see around here because it did not make any, it barely detected at the anisotropy in temperature. So after 30 years, this field has advanced dramatically, orders of magnitude improvement. Right now we are here. So what are we doing right now? What are we pushing next? Apparently we are pushing to more and more sensitive measurement, lower and lower noise. So this is exactly what we are doing. We should improve the sensitivity and lower the noise. That's the future advancement of this field. So, and then the noise I'm writing down here as the equation, the measurement noise it has mainly two components. One is instrument noise. The other one is the photon noise from the statistical noise of the incoming signal. So after generations of instrument development, right now the CMB detectors operating at less than 1 Kelvin, no, not less than 1 Kelvin, less than 0.1 Kelvin, normally almost 0. So the noise from the detector and also all the readout electronics is so low that it's the entire measurement noise is actually dominated by the photon noise, the statistical noise from the incoming signal. So that's kind of a problem, because no matter how hard we work on the detectors, on single one detector, we cannot improve the noise anymore because it's intrinsic in the incoming signal. So what do we do with that? So the choice is we try to increase the integration time to beat down the statistical noise. So we can observe for hundreds of years, or we can deploy simultaneously more detectors on the sky. That's actually the fundamental reason why this current CMB experiments are going to this mega scale. Simon's Observatory CMBS4, which will be deploying tens of thousands of even hundreds of thousands of detectors simultaneously, basically to increase integration time, to beat down the noise, to increase sensitivity. And then, however, if we could ask the question whether the photon noise can be reduced at all, the answer is not strictly no, because the photon noise is related to the incoming radiative power. So not all power from the incoming light is actually the sky signal we really care about. And I made a little analogy here. So I'm looking at the Mickey Mouse on my mug through a pipe. So if the sky signal we really care about is the Mickey Mouse, a significant fraction of the solid angle is actually taken up by this, the wall of the pipe. This is the, although we don't care about it, it gives us this loading, which will eventually contribute to the photon noise. So if somehow we can eliminate the loading from this unwanted solid angle or sources, we can essentially reduce the photon noise. That's the basic idea here. But how can we do that? First, this wall has to be low reflection because it cannot reflect radiation from the outside to begin with. Also, by controlling the reflection, we can reduce the beam systematics. Rather having all these beams bouncing around in the telescope, having them all controlled, terminated is always a good option. And also, the material, the surface itself will emit because it's a black body, everything emits. So how can we control that given the Stefan-Boltzmann equation is sigma t to the 4th? So it's helping us a lot. If we can reduce the temperature of the surface, it will significantly reduce the loading from its own emission. So if we imagine instead of at 300 Kelvin, like room temperature, if we can cool it all the way down to 3 Kelvin, 2 orders of magnitude in temperature, it can help us 8 orders of magnitude in its loading itself. So in total, low reflection, low temperature, it basically gives us the answer as cold blackbody. And then here's how we can implement this kind of a toy model thing in our scenario. So this is why I said it is a tube. So similar to this, this is the optics tube. We have 13 of those. And then this is the detector. It will be similar to my camera where I took this photo. So if we look out, it's not as simple as a tube looking at my Mickey Mouse. It is very complicated. So it has lenses, filters, lenses, Leo stop, lens again, filters, etc. So instead of just doing a simple calculation, we need a comprehensive simulation to see which part we need to blacken will give us the most significant improvement. So that's why we did this optical simulation comprehensively to show that it is this front section, which is red boxed here, that will significantly reduce the unwanted loading. So basically the simulation shows if we leave it bare as a bare metal compared to have it well treated with cold blackbody, we can increase the sensitivity by a factor of 2 just doing this. So and then what the material should be like, what property this either coating or whatever material should have. So first, to be a cold blackbody, this thing should be thermally conductive, because if it's not thermally conductive, we cannot guarantee that the surface of it can be low in temperature. Also, it should be a blackbody. It should have low reflection, as we mentioned in the previous slide. And one more thing is, because it's backed by a metal wall, if it is very transmissive in the radiation we care about, it's almost like reflection, because the radiation can go through it, bounced by the metal wall, and come back. So it has to be very absorptive as well. So that's kind of the requirement: thermally conductive, low reflection, high absorption. This thing is not a new thing. The CMB field has been facing this problem for years. So the previous solutions are either using carbon-loaded epoxy. So in reality, it would be like a starry cast loaded with carbon or probably even steel powder or something. So because of the dense material, it does have a really good thermal conductivity. It can guarantee the surface will be cooled to 1 Kelvin, 4 Kelvin, or whatever. But because of its high index of refraction, the hard boundary for the electromagnetic wave, it does reflect and also scatter a lot. So, and there is also another alternative. So it's not ideal, basically. So there's another alternative, which is using absorptive sheets. There are even commercially available ones called Aquasorb, HR10 or 25. So these have very good optical properties. They reflect a very little amount and then they absorb. But because of this, because it is the foamy thing, that's how they kind of impedance match between the free space and also this material, the bulk material. So it's really hard to cool the tip of this material down. So that's also not ideal. That's why we came to our solution, which is using the concept of metamaterial to develop our metamaterial microwave absorber. The work is published early this year. So this is how we do it. So basically, we use a carbon-loaded plastic. So it's carbon-loaded. It's a plastic. So it is very it's absorptive, and also because it's a dense material, so it's thermally conductive. And then, but if we just leave it as it is as a carbon-loaded plastic, it will have the same problem as the conductive loaded epoxy, given its high index of refraction. That's where this anti-reflection, metamaterial anti-reflection coating comes in. So you can see this is a piece we designed, and then this is the surface. This surface size is about like 1 inch times 2 inches. And then if we zoom in into one of this part, you can see it has this small, fine pyramidal kind of structures. If we zoom into one unit, it looks like this. All the parameters were kind of optimized for from simulation. So conceptually, how this works is for the radiation we care about when it comes in, these features are sub-wavelength scales. So when the radiation comes in, it won't be able to distinguish the fine details of this structure. What it will see will be like a little blurry, fuzzy kind of a blur with a gradient index of refraction, basically matching the impedance from free space and the bulk material. It basically eases the radiation in without bouncing it away. So then once it's into the material, its high absorptivity will absorb the radiation immediately within millimeters. So that's basically the idea. And then in reality, there were more problems we need to address, which is because of the unmatched thermal coefficient of thermal expansion, CTE, from metal, which is where we will be bolting this down, and also this plastic, we can only have one fastener for one tile, otherwise it would tear it apart from thermal expansion or contraction. So, and then if we can only have one fastener, which is also one thermal contact, we also want to control the thermal gradient for one piece. This piece cannot be very big. So that's why it is this 1 inch by 2 inch size. And also this anti-reflection surface works rather well with low incidence angle, but it does not work very well for glaring angle. That's why we tilted the surface to make sure this works. For the we are using its maximum optimal performance for our applications. And then from the very beginning, we know we will be needing a lot of those. We will be needing thousands of those pieces. So we have to make sure they can be manufactured at low cost. That's why we found this injection molding process, which once the mold is made, we can just pop this out with very low cost, like negligible amount of money. So, and then once the prototype were ready, we can do these tests, all kinds of tests. First of all, this is a plastic. When thermal cycle a plastic across hundreds of degrees, a lot of them just break. So we dunk tested this in liquid nitrogen and they survived. That's level 1. And then level 2 will be the thermal conductivity, thermal properties. So then this is the testing setup. On the left is a cartoon. On the right is the real thing. And then different rules are viewed from different perspectives. You can see we have thermometers here, the brown thing on the left, on the right, and also one on the center. So on the left and right are the kind of the farthest away from this anchoring point, this pressing nut. And then the reason we put one on the top is basically we were always worried, even in the design, that the tip of the pyramids, which receives most of the radiation and has a kind of a weak thermal link to the bulk material, whether the tip will cool. So that's why we bolt and also glued one thermometer on the tip of the absorbing surface. So, and then to get a kind of a dynamic range of the thermal conductivity, we also stick in a heater, a resistor actually, into the back of it. So because there is a pocket, so the heat from the heater will have to go across the entire structure to go to the thermal anchor point. So that's the overall structure, and then let's see the result. So these thermometers have some like absolute calibration accuracy, but it's very sensitive. They are very sensitive in relative changes. So basically that's why when there were no additional power on it, they have some like a original offset. But as we add additional power on this resistor, you can see at some point all of the thermometers started to tip up. So then we need to ask ourselves, in reality, what would be the loading? What the loading would be? So basically, we did a calculation. So right now, things are during this test. This piece is actually in the environment of 1 Kelvin radiation. So and then we say, okay, this is 1 Kelvin. Let's say we do a conservative estimate. If this entire thing is immersed in a 4 Kelvin environment, what the loading would be if we assume this thing is entirely black body, absorbs everything that goes onto it. It's about 40 nanowatts, so which sits right around here. So basically, this demonstrates that this thing will cool down within the radiation environment that it will be used. So that's the thermomechanical test. And then the more important one is actually the optical test. So here on the left is the reflectivity measurement at different incidence angles, 15, 30, 45, 65, 60 degrees across different frequencies. And then you can see, if we look at this, they are mainly all below 30 dB, except for 60 degrees angle of incidence and not even 65. So that's actually the very reason we tilt the surface, basically to avoid dealing with this large angle of incidence. So another kind of interesting test we did was actually we compared a piece without the metamaterial anti-reflection coating, so which is this purple triangle here. And then compared with the same angle of incidence, which is the blue crosses here, you can see this is actually a demonstration of how effective this metamaterial anti-reflection coating it is. So you can see it suppresses the reflection by more than 20 or probably even 25 dB. That's a cool test, we think. And then we also measured the scattering, because some of these some of the solutions we tried before is it doesn't reflect exactly at the direction of the incidence angle, but it does scatter a lot. So the problem for that is it does not give us a kind of a ghost in the beam maybe, but it gives us a kind of a haze, which we also want to avoid. So that's why we measured the scattering for different incidence angle, 15, 30, 45, 60. So we don't see any kind of a spike in kind of this scattering, which is as expected. So they are all kind of within 30 dB, minus 30 dB. So you can see we have this TK as a reference here in the measurement. TK is kind of like a reference observer we have in this field. But the problem for that is TK is really expensive, and also it's not very easy to customize for different uses. So the fact that we are doing even better than the TK is a really satisfying one. So basically we are achieving what we were planning or even beyond. So, and then talking about the previous kind of the wedge-shaped thing was designed for the Sciene Observatory, but this technology is really highly customizable. So you can see we also made this square version for more general use. Each of this square tile is about like 1 inch times 1 inch. And then you can see it can be, you can see this is from the front. You can see the absorbing surface is very black, even in optical. This is the back. And also to cover a wider area, we designed this tessellating features into it, like a tessellating tip, tessellating dent, and also the screw head recess, screw holes. And also if we also took a picture of the fine structures under microscope, you can see the injection molding really recovers these fine features rather well with low cost. I want to emphasize that each of these pyramids are only 0.6 millimeters apart. So it's very fine features that this process can maintain. And also this, not even to say, this injection molding process reduced the cost by a factor of 10 from this technology. So, and then even though this is developed for the Sciene Observatory, after this technology came out, CCAT Prime and also CNBS4 has implemented this technology for their instruments. And also several other CMB and also millimeter experiments have shown interest in this technology. So beyond, this is really something we did not anticipate is we received a lot of recognition from this work. So after submitting our paper to Applied Optics, the publishing company, OSA, the Optical Society Publishing, decided to do a press release for this paper. And then this paper was also selected as editor's pick. And it's also reported in the UPenn News, Penn Today, as you can see here, and also Physics World. So so I think something would be fun to do is, so I've been talking about this on slides all the time. So I actually, when I was working on this, I actually took a time-lapse video of me installing all these 240 tiles into one optics tube. I tried, it will not go through very well through Zoom because it goes very fast. So instead, I think I can share a link of this video in the chat in case you are interested to click. And then you can see me basically dancing around how to install this, have a kind of tangible feeling of what these things are and how it looks like. So, and also this also kind of brings me to the end of my talk. So basically the conclusion is over the past 30 years, the CMB field has made dramatic advancement in measuring the frequency spectrum and angular anisotropy for cosmology and astrophysics studies, and with much, much more to come. So to further reduce the measurement noise, we developed this metamaterial microwave absorber to reduce the radiative loading and suppress beam systematics. So the tiles have been tested for thermal properties and optical properties and are highly customizable for different applications. This technology has been implemented in several leading experiments with more showing interests to implement that. So here is all I have. Please let me know if you have any questions. Thank you so much.
Wow. Okay. Well, thank you, Zhilei. That was really neat.
Thanks.
So I have a initial question off the bat is, you said that they've been utilized in other instruments.
Right.
Have those instruments been deployed or used for observations thus far?
No. So because if it's that stage, that'll be too late, right? So the CCAT prime is actually it's kind of like a sister or brother experiments for the Sciene Observatory Large Aperture Telescope. So so they are still kind of under development, probably even a little bit behind the Sciene Observatory. And CMBS4, as you can probably heard about, is it's a very kind of a decadal survey level experiment, hundreds of millions of dollars. So it is still kind of on an early kind of design stage still.
Right.
But these are all on there. So when this came out, it was like, oh wow. They were like, oh, I wish you guys did this earlier so we don't have to, because this has been a long time pain for everyone, because the previous solution, either you have to use this kind of carbon loaded epoxy all over you and apply it. It's very messy. So, and also it's not very effective. So, and then, so when this came out, when we really, so to test these that can cool, has this optical property, we really have to leverage a lot of resources. Like we have to have a dilution refrigerator, which is really lucky. Professor Mark Devlin has that in University of Pennsylvania, which is tested easily with a facility. And also for the optical property, we worked with our collaborator at the University of Chicago, Jeff McMahon, and also the second author on the paper, Grace Chasmore, who is a student at Chicago, basically measured these optical properties rather well. So it's so I think it's not hard to come up with something, but it's kind of hard to have all this kind of facility to test things out. We can say, okay, this does cool, don't worry, and this does not reflect. Because when things are all implemented, these tens of millions of dollars instrument, you say, oh, wow, probably doesn't work. There were thousands of reasons things didn't work, whether it's this or that. So people wants to make sure things put in, at least as far as we know, should not give us problems. Otherwise, there will be too many kind of, what is that called? Floating things to press down. Too many problems to solve, too many factors to eliminate.
Yeah, too many things, too many uncertainties up in the air. That
yes, yes, exactly. Thank you, Jesse.
All right, well, does anybody have any questions right now?
Zhilei, I had a question.
Hey,
John Wilson from UVA. Congratulations on this work.
thanks.
I was curious, usually plastics are avoided in ultra high vacuum and high vacuum because of molecular outgassing. And I'm just curious how you, if that has been an issue for you coming out of the plastic.
No, it didn't. That's a good point. So you can see when we are testing this, they are all in this. They were for the individual ones tested it. They are all in this dilution refrigerator. For that single one, of course we didn't see any outgassing and noticeable. And then probably that's not sufficient because it's only one. We will deploy hundreds or even thousands of them. So right now they are already put into this, like I show in this video, in the optics tube, hundreds of them. And then we put them into the cryostat, the large aperture telescope cryostat, the 2-meter one. Already, we didn't see any outgassing. That's a good point. I should emphasize. We were concerned about this.
Thank you.
Thanks. No problem. Great question. Thank you so much.
Can you go to your picture of the tube of the detectors?
Of course. This?
Yeah. So I came in a little bit late, but sorry, this is not
No
relevant,
problem.
but I was wondering, so that 40 nanowatts you mentioned earlier, as far as the thermal loading to the absorber,
Yes, right.
is that encompassing a full black body spectrum, or is that like a segment of that? In other words, if you have a IR absorbers out front of the absorbers, or IR filters, I mean.
Yes, it's including the entire spectrum. We also consider, yes, we also consider the transmission band of all the IR blockers, right? Okay,
thank you.
No problem, thanks. Great question, thanks. These are all the details I don't have time to get into. So to follow up on this, it's actually, you can see this actually works much better than we thought, right? So we will be happy even if it tips up around here a little bit. So, but it's doing better. And also, these measurements were done with just a single piece. So right now we have hundreds of them being kind of like deployed already, and then we don't see any problems of them. So that's actually another level of confirmation that this technology will work. But when we were writing this paper, we didn't have hundreds of them deployed in a real cryostat.
So you actually have a lot more data to back up now.
Yeah, I would say it makes our makes our statement more confident. So, but but I think yeah.
Well, go ahead.
Zhilei, how many or what fraction of the total number of absorbers that you need for SO do you have?
Hey Charles, nice to see you. Good question.
Yeah.
So for each tube we need 240. We have 13 tubes, so you can imagine we need 1,000. So I think we've already bought 10,000 of them, and I have used up because no, we bought like 5,000. So if you click the video, when I was installing them, I did all 7, I think, already. Oh, I think the first batch we bought 2,000, and I ran out of them.
Oh.
You probably saw them, Charles, when you were here.
Yeah, I do remember them.
Right. Yeah. Yeah. Thanks.
Yeah.
Wow, that sounds like quite a pain, but a relief once it's done. So do you have any plans to upgrade this material in any way between now and when it's actually needed?
For Science Observatory, probably not, because everything is already done. For future experiments, because the CMBS4 is still under development, so probably we can do more, because one thing we were concerned about is how well this works in very low frequency. We were confident that it will work well by measuring some dielectric properties, but we did not have measurements for the reflection and also scattering measurements. So, but this is the direction of development. We will probably beef it up in the thickness or something.
Yeah, that was another thing I was curious about, is whether or not you can take this idea and manipulate it to varying frequencies.
Yeah, that's the idea. So if you look at this, where is it? It's actually, it comes down to these two parameters of these pyramids, right? So roughly speaking, the height is more complicated than this. The height basically determines the thickness of the AR coating, kind of determines the, I think it's the lower limit of the frequency that it will work, and it's the pitch that determines how high it can go. You can imagine, because it has to be sub-wavelength, right? So it has to be sub-wavelength. If this scale is similar to the wavelength, it can distinguish this thing will not work very well. And then you can imagine, ideally, we can have a very small pitch and a very long height. That would be ideal. It works for small frequency, it works for low frequency, it works for high frequency. But in practice, it's really hard to make these high ratio pyramids given this injection molding, because if it's like a pole, it will just not render in the injection molding. So this, right now we have is kind of a 5-to-3-to-1 or 5-to-1, you can call it, is already kind of pushing the limit. So
okay, so better ways of actually creating the plastic material would be needed.
Right. So yeah, but yeah, I think this can definitely be tuned for, say, more of a GBT, because it's actually the fine structure that is really hard. If you say this can be proportionally enlarged by a factor of 5, so it can work at gigahertz or maybe even 100 megahertz, I think it'll be much easier. We can make the tiles bigger, it will be cheaper. Yeah, so I think it will be easier if there were interests.
Well, something to look forward to.
Yeah. Thank you.
All right. Well, I think we're pretty much out of time. So if anyone has any more questions, feel free to get in touch with Zhilei. Otherwise, let's thank him again for this awesome talk, for joining us today. Thank you very much.
Thank you for having me. Have a good one.
Of course, everyone, take care. And for those who are interested, next week we'll be having a talk with Trey Wenger on the structure in the Milky Way with galactic H2. So take care, everyone.
Thanks, Zhilei. Good seeing you again.
Good to see you as well. Thanks.
Thank you.
Bye.
Great to meet you.
Yeah, good to meet you as well. Bye.